So now that we've talked about categorical data and some of the things that we can do with it, I'm going to now present some words of caution and why people often get confused with statistics and how do you implement it. So when we are drawing a picture for any of our graphs that we are making, people say that pictures are worth 1,000 words. But words can be perceived by the reader, and you may be influenced by how the picture is presented. So just take, for instance, this is a picture of wins by certain baseball teams. And just based off of the size of this bar graph, you can see a distinction between the Blue Jays and the amount of games they won versus the Dodgers. But if we just subtly change the scale on the y-axis, and now instead of going from the maximum of 30 to the maximum of 100, to a maximum of 100, you can see everything gets squished down. It's still the same data, but by changing the scale, we've now altered and compressed everything in to it looks almost indistinguishable, versus we were clearly able to see in this one that the Dodgers were about 11 games behind the Blue Jays. Likewise, if I asked you, presented this chart, and said, who eats more cantaloupe, men or women? It's hard to tell that these are drastically different. The male is a bit over 1, and the female is still under 2. You can see that they're different. But what takes your eyes are the sizes of the cantaloupe. So the observer sees everything in 2 dimensions. But the only dimension that's relevant is the horizontal, the height of each of these. So it's clear. You have to ensure that the area principle of the display has an appropriate proportion. And with a lot of these graphs that I will continue to show you guys, they try to make things more complicated than you need to. So make certain the display is complete. These things are essential for anything that you create for this class. So every graph that you create should have a title explaining the subject. You need to label the horizontal and vertical axes, label them clearly and completely, properly scaled and labeled. If you omit information or information is missing, so if you are missing labels, you are not providing that information. You do not want the person that's reading this. Just think down the line if you're taking the AP test. They're not going to assume you know what you're doing. So be as explicit as possible. Make your graphs as large as feasible. Don't just be like, I got a small piece of paper that I'm trying to fit this on. No, make them so they're legible. Larger allows for greater accuracy. And any graph reproduced from another source must include a source reference. I know I am guilty of neglecting sources, but I'm not publishing, so I forgive myself. Okay? But if you are going to write a research paper down the line and you're going to use someone else's work, you need to source it. So some things not to do, specifically for this class. If you want to save those for the business world or future presentations, fine. But in statistics, we are going to keep it simple. So do not violate the area principle. So in other words, do not get cute. I know there's software that can turn a pie chart or a bar graph horizontally, make them 3D, but we're losing this area principle that we highlighted in the first part of the chapter 3 notes. So while some people might like the visual of the pie chart on the left, the one on the right is better because it's the 3D version is much more difficult to compare fractions of the whole. And that's the primary purpose of a pie chart. So don't try to be cute. Simple as that. What else shouldn't you do? Make certain your display is honest. Your numbers might not be lying, but certainly if you don't represent it accurately, there will be a problem. So make certain your display is honest and not intended to fool the reader. Your display should show what it purports to show. So if you look at this, this is looking at the percentage of high school students who engaged in specific dangerous behaviors. And if you notice, it has a few problems. And I would normally ask in class, what do you see is wrong with this? Besides the fact that it's a three-dimensional graph, so it's not accurately showing the proportions, clearly what's a problem is that 50% is not actually 50%. Additionally, 26 and 31.5% should be slightly closer than what they appear to be. This is deceptive to the reader trying to gain some sort of insight into this graph. So don't do this. How about another one? So does this make sense? This was asked to 5,387 people. How common is red hair? If we look at this chart, we have fair, red, medium, dark, and black. So if we're just looking at red hair, it's not all too common in the total. But I have a question for you. What does fair mean? I mean, like, seriously, could fair be blonde? Could fair be red? If you're unclear about what the distinction is between these two, we're losing a lot of the data that could fall in for red hair. And so it all depends on what you mean by fair. If we're looking at these proportional percentages, so the relative frequency chart, you can see that if we combine these two together, it increases the count. Now, this data was from Caithness County, Scotland, so you would think red hair is a lot more common. As I said in the first video on data, it's not that statistics lie, it's people do. And we often misrepresent our data with the charts that we use. So I want to go over some ways that people misrepresent data. So I contend statistics do not lie, but there are people who will, intentionally or unintentionally, and they're trying to mislead you. And this is especially true of using graphs, and you'll see them across news articles all the time. So view graphs through a knowledgeable lens. Be a little skeptical. Always ask how the data was collected, from whom the data was collected, when was the data collected, where did you get your data, and most importantly, why are you being shown the graph? Por ejemplo, for example, do you see anything wrong with this chart? This is from the 2011 Bureau of Labor Statistics showing the unemployment rate for our previous president, under President Obama. Now, if you look at this, is 9% the same as 8.6%? I think you will all come to that same conclusion that those two numbers are different. But if you solely based your information off this charts, they look like the unemployment rate has not changed. If we actually accurately represent the data, you can start clearly seeing a downward trend. So note the scale along the vertical axes. It should be consistent. How about this next one? Here is a percent who agree with the decisions from the Supreme Court. Now, when was this taken? We don't know. So it's not said on this chart, which is a problem. But if you look at this, oh my gosh, it looks like the people that lean Democratic are 3 times as likely to support or agree with the court than Republicans or independent. But this is 54, and the Democrats are 62. So once again, if you note the scale along the vertical axes, it's being misrepresentative of what the data is actually representing. Likewise, here is an image about a chart representing the overall rise in global warming. So this graph reveals how 95% certain estimates of the Earth heating up were a spectacular miscalculation. And what we're seeing is this black line is the trend line that people are making the argument with. And if you look right in the 2000s, it looks like if you wanted to follow the trend, that it's going to fall outside of the predictions. But note, the dark red band is what 75% with with a 75% degree of certainty that we can be sure of that. With a 95% degree of certainty, so more certain but a wider range, is this lighter color. And this black dot, all of the data still falls within that 95% degree of certainty. So we don't make future predictions based off of past data without developing a reliable model. And note, we're still inside that 95% prediction. Second, this graph shows air temperature. And if we're talking about global warming, you might want to think, what about ocean temperature where most of the heat resides? And third, and most importantly, we never trust extrapolation past data. We don't know what the future holds. We have no knowledge of what comes next, so we don't extrapolate. Be careful about that. It's one of those logical fallacies that we're going to push against in this class. Another way of looking at this, sometimes when you start your data with the y-axis at 0, it hides important changes. So again, on global warming, if we just showed the temperature starting at 0 degrees and we looked at the average annual global temperature, it looks like it's not changing. But that's deceptive because subtle changes in the Earth's temperature, we're talking about 2 to 3 degrees Celsius or 4 or 5 degrees Fahrenheit, have drastic impacts on our life around us. So it's important that if we know what the data needs to be more specific, that we zoom in on that to look at what is happening and to analyze if there are any trends there. So to put it in a different way, what happens if we measured Sarah and Bob's body temperature? Like we're walking into school, measuring our temperatures. If you compared the blue and the purple lines, they look roughly the same. If you had a temperature below 95 degrees, you are not alive, or you're more likely a popsicle. You're frozen. But again, if we zoom in to the relevant temperatures, where we want someone between 97.5 degrees and 99.3 degrees, and anything over 100, you have a fever. Now we can start actually seeing who has the fever and whose temperature is somewhat regular. Obviously, Bob has significant spikes. So by changing the scale on the y-axis, now we can see it. Other ways of potentially confusing people by giving the 0 part. Let's look at the US GDP. Both of these are over time, starting in 2004 to going to 2012. If we set the bar at 0, it doesn't look like the GDP changed all that much. But if you can think back 12 years ago, when many of you guys were 6, there was something that changed in 2008. 2008 to 2009, we had this big fall off. That was the Great Recession. And then our economy slowly started growing back. So previously, in the past decade, the economy was a mess. But if you look at the gross domestic product, it was flat. But by zooming in, we can see that there was some recovery efforts happening post-recession. A few more, and then we'll call it for this video. So, is college a bad investment? If I just looked at this chart, and it's analyzing the diminishing financial returns of higher education, going from 1964 to 2010, we're comparing tuition and room and board at universities to bachelor's degree earnings of a 4-year degree. Now, you might be asking yourself, what about the earnings of those not attending college? Are those in this data set? Maybe the differential is worth the investment. Who knows? So in this graphic, the cost of a 4-year degree is compared directly to the average first-year salary. And that's not actually a valid comparison. If you want to truly determine the value of a college education, we have to compute the expected increase in earnings over not going to college after a lifetime of work. And if we're not computing those things, then it's not an apples to apples comparison. Last one. We have a couple good ones. If we look at this chart, welfare versus full-time jobs, and this is from the Census Bureau from 2011, if we compare people on welfare to people with a full-time job, it looks like, just from this bar graph, that there's way more people on welfare compared to working, just using up government resources. But it's important to know what is represented in those numbers. Does anyone actually believe there are 7 million more people on welfare than there are working full-time in the United States? That is a very hard thing to believe. So if you go a little deeper into how they actually collect the data, full-time jobs counted only persons actually with a job. Versus, to get the welfare number, the expert at the Bureau of Labor and Statistics counted every person in the household in which any person received benefits. Thus, also counting individuals that actually received no benefits, people that live in a household. We're not separating those two. So we're getting these larger counts for maybe one person receiving benefits. Again, this is a classic apples and oranges comparison. They're not the same. So it's deceptive, but it sure looks official. 2 more. We'll get to my favorite ones. Other drastic worries. If you look at this chart on the left, you see that the government is spending all of our money and they're stealing it. But do you actually know what it represents? So like this pie chart reflects only discretionary spending. Those are monies that are not already committed. If we actually put in all of the money that's already dedicated, this chart reflects both mandatory and discretionary spending. And when you start hearing people in government, especially, saying that we need to cut the fat, well, though a lot of these programs that are taking up the budget, like education, is only 3% of our national budget. And what's taking up a large portion are Social Security, healthcare, and defense spending. But we know that the military is 57% of the discretionary spending. All of these other programs are very minuscule in the way that our government allocates money. Last 2, personally, these are my favorites. This came up in a news article. So if we're looking at graduation rates, people want to say graduation rates are improving. Just look at this. What is wrong with this chart? Besides that it's trying to be too cute. My question to you is, what does a book represent? How much is a book? If you count 1, 2, 3, 4, 5, 75% has 5 books. So is one book 15%? Then do each of these charts that adds more and more books, is that actually representing what we want? So there are several problems with this graph. So they're too cute with the illustration. Don't do this. The books are unnecessary because then it loses what the unit value is. So if 5 books are equal to 75%, so one book is 15%, 82% should be just 5.4667 books. And that's not how that bar chart is displayed. How it should look is the one in purple. And you can see that the numbers are going up, but more slightly. But the most serious problem is that the bar chart is not the appropriate graph for this data and what it intended to show. What you should have looked at is a time series graph because we're looking at things over time. So when the goal is to show changes over time, it is preferable to use a frequency polygon, or people call them line graphs or line charts. So yes, if you look back, graduation rates this past decade did increase during Obama's term, but that increase had begun around 96 during the Clinton-Bush presidencies. And my all-time favorite graph, and then we will end this video. This is from Florida, and it's trying to represent gun deaths in Florida. But it's trying to spin it in a positive way. So if you look at this chart, what is the y-axis? Well, the y-axis is showing you the number of murder deaths. What you should do, and the only explanation for this graph, is it's an intentional attempt to mislead the reader because you think the lower numbers are good. But in fact, it's inverted because numbers go up. And so if we invert this graph, we can see that the gun deaths in Florida are quite high and still rising. So that's the end of categorical data. We have one more unit or one more chapter that we're going to cover this week, and that's going to introduce us to quantitative data.